So we're going to talk about compounds that contain some really important elements: oxygen, sulfur, and halogens. Okay, so I wanted to kind of intro this whole chapter with an aspect of one particular molecule. So if you look down at the bottom of the slide, this is ethanol. Okay, we're all familiar with ethanol. It's the alcohol in alcoholic beverages. This is what it looks like. Our body metabolizes it and breaks it down. I'm going to show you that on the next slide. So in pregnancy, though, I thought this statistic was really astounding. 1 in 10 pregnant women in the United States report drinking alcohol in the past 30 days. And what that can lead to, and there's no safe amount from what they've determined. They just say it's best to abstain. But what that can lead to is it's the leading cause of birth defects in the United States. And here's why. Okay, so it's known as fetal alcohol syndrome. The placenta, the amniotic fluid, nothing is a barrier to ethyl alcohol. Okay, our body has enzymes that are responsible for breaking down, metabolizing ethyl alcohol, and those are shown right down here. But infants and fetuses, it's not that they don't have these enzymes, but it's that these enzymes aren't functioning at the capacity that they are in an adult. So here's what happens in an adult. Okay, you've got ethanol, ethyl alcohol right here. And this is a really important enzyme, alcohol dehydrogenase. So think about, we talked about hydrogenase or hydrogenation reactions yesterday, all right? With hydrogen, right? We're adding hydrogen when you do a hydrogenation reaction. So a dehydrogenase means we're taking hydrogens off, okay? So what it does is it takes this alcohol right here, this is the alcohol functional group, and it breaks it down into this, okay? Do y'all recognize this? This in particular is a new functional group. Do y'all recognize that functional group? Okay, so that's an aldehyde. So it breaks it down from an alcohol to an aldehyde. And then even further, you've got an aldehyde dehydrogenase. It takes more hydrogens off and it makes it into a carboxylic acid. Okay, and that's what's explained down here. It's a two-step process in the liver. That's where things are broken down. The first enzyme, alcohol dehydrogenase, we call it ADH for short, breaks it down into an aldehyde and then finally into acetic acid, which is a carboxylic acid. Okay, we haven't talked about carboxylic acids yet, but that's the end result, and that is a safer molecule for our body than the alcohol, okay? So we're not gonna have the same effects from acetic acid that we would from ethyl alcohol. So the problem is that the activity of ADH, our enzyme here in the liver of a growing fetus, is less than 10% than that of an adult. And they don't have near as much because they're a growing fetus, okay? So anyways, I kind of want you to be familiar with the enzyme responsible for this. If I see a question about it on the exam, and the significance of it, okay? Now, alcohols aren't all bad, okay? In fact, I would argue that alcohols are one of the most important functional groups physiologically, okay? So, yeah, this is a bad aspect of it. This is a sad thing, but alcohols are a really, really important physiological or functional group when it comes to our bodies and what they do. We're gonna be talking about alcohols for the rest of the semester. So let's actually look and define how we differentiate between alcohols, phenols. We learned that word yesterday. Okay, a phenol is an aromatic ring, right, with the OH group on it. And then ethers. Okay, so you guys probably remember I mentioned ethers Tuesday. We're really going to dissect them today. That functional group is the carbon-oxygen-carbon sequence, and it's single bonds. And I told you it's really easy to get ethers mixed up with esters. Okay, so later we'll talk about esters, but today just remember it. A carbon, oxygen, carbon single, and that's the ether, okay? We call just an OH group, just the group itself, we call that a hydroxyl group, okay? But when it's bonded onto a molecule, it makes that molecule an alcohol, all right? Now, how do we differentiate these? What are some properties that kind of are associated with alcohols, phenols, and ethers? Well, so alcohols are structurally similar to water, right? It's like 2/3 of a water molecule. You have the oxygen and the hydrogen, okay? So you've got this positively, if I erase, if we zoom in on this hydrogen is positively polarized, and then you got these lone pairs on this oxygen, right? So we have everything we need for hydrogen bonding, okay? So they're very structurally similar to water, And due to that, many alcohols share similar physical properties with water because they look like water. Okay, so they're going to behave like water. Now, I want you to look at this figure. We're going to examine how this affects physical. When I say physical properties, what do I mean? When I say physical properties, I mean like boiling point, melting point. Is it a gas or is it a liquid at say, room temperature? Things like that. And that all has to do with everything from chapter 8, intermolecular forces, the hydrogen bonding, the dipole interactions with London dispersion. Okay, so here we're mainly examining, can these molecules hydrogen bond or not? The stronger the type of intermolecular force holding molecules together, the more energy it takes to break them apart, the more heat. Okay, so the higher their melting and boiling points will be. So look at this, ethyl alcohol. Guess what? We've got the acceptors right here, and we've got a donor. So this can hydrogen bond. Alcohols can hydrogen bond. Okay, what do y'all think about dimethyl ether? This is an ether because we got the carbon, oxygen, carbon sequence. Could this hydrogen bond with itself with another ether? So here's what I noticed. We've got the lone pairs. But do we have, these are the acceptors, but do we have any donors? Do we have any positively polarized hydrogens? No, none of these hydrogens bonded to carbon, those are non-polar bonds. Those are never positively polarized, okay? So none of those are donors, all right? So we have an acceptor, but we don't have a donor, so it cannot hydrogen bond with itself. It could interact with the water molecule, but not with itself. Okay, look at propane. The reason why I threw why this figure throws propane in here is because we're trying to examine different molecules that are similar in size. So you can see MW stands for molecular weight. So these molecules are all similar in size, but you can see just beneath, what do y'all think BP stands for?
Boiling point?
Boiling point. Look at their boiling points. They're all pretty different, okay? And alcohol can hydrogen bond. So it boils at 78.5 degrees Celsius. Do you guys know what room temperature is on the Celsius scale?
Is it like 32?
Body temperature is 37. Okay, so it's room temperature, like probably my office right now, probably the classroom you're seeing is about 20 to 21 degrees Celsius. So relative to that, 78.5 degrees Celsius is super high. That's super high. Okay, so it takes a lot of energy, a lot of heat to boil or melt or break apart these ethyl alcohol molecules because they can hydrogen bond. On the flip side, ether molecules cannot hydrogen bond. So look at their boiling point, negative 23 degrees Celsius. That's drastically different. Okay, you see how it affects physical properties depending on whether you can or can't hydrogen bond. Same thing with propane. Gosh, its boiling point is even lower. This is a gas for sure, 100% at room temperature. Okay, water though. Look at its boiling point. We know water can hydrogen bond. Water can hydrogen bond multiple times with one individual molecule. So that's why it has the highest boiling point, 100 degrees Celsius. Insanely high, right? So the high boiling point of ethanol, which is the alcohol here, is due to its ability to I'm going to abbreviate hydrogen bond. If you are still lost on hydrogen bonding and how this works and how this plays out, please take some time to review section 8.2. Okay, it'll walk you through it step by step. This is stuff covered in a previous course, so I'm not going to take the time to get into it, but that's what all of this is built on. All right. So now that we've identified these, I want you to look at this slide right here. I want you to tell me, we're going to do all 6. We're going to identify each one as either an alcohol, a phenol, or an ether. So what do y'all think? What about A? Is this an alcohol, a phenol, or an ether?
Would it be an alcohol?
Yep. Okay, here's the OH group. And we don't have any sort of aromatic ring. We don't have any carbon-oxygen-carbon bond. So this is an alcohol. Okay, what about 2? Abby says phenol. So there is the aromatic ring, but a phenol is specifically an aromatic ring bonded, well.
Would it be an ether?
To an OH, okay. So let's expand, okay, yes, Madison, let's expand what's going on with these. So we got, this is a This is a carbon right here, right? And it's bonded to an oxygen, okay? And then it's bonded to another carbon. So we have a carbon, oxygen, carbon sequence. Okay, so I don't blame you for guessing phenol because that aromatic ring makes you want to think that. But when you break down the bonds, this is an ether. Okay. Okay, now Abby, what is 3? It's your moment. Look at her. Phenol, okay? You got the aromatic ring directly bonded to an OH group. All right, what about number 4? We have a ring structure, but is it aromatic?
Would it be alcohol?
Correct. Okay, so this is not aromatic. It is cyclic, okay? It is a ring structure, but it doesn't have alternating double single bonds. So it's not an aromatic. Robin.
Okay, so a phenol is going to have an aromatic.
Yes, it's got to be an aromatic bonded to an OH group.
Okay, that'll help me. Okay, thank you.
Yep, so this is an alcohol because you have a carbon bonded to an OH group. Okay, okay, 2 more. What do y'all think about number 5?
Is that an ether?
Claire, it is. So this carbon right here, we got a carbon, oxygen, carbon sequence. Remember this hydrogen right here is going to either be branched up or down. In the condensed structure, we write it all in one line, but it's branched up or down. So this is an ether. And then lastly, what do y'all think about 6?
Would it be a phenol?
So we do have an aromatic and we do have an OH group, but this is kind of specific. So remember a phenol, the OH group is directly bonded to one of the carbons in the aromatic. Okay.
So would it be an ether?
An
No.
ether must have a
No.
carbon, oxygen, carbon sequence.
Yeah.
So by process of elimination, everyone, this is a what?
An alcohol because it's a OH group connected to a molecule.
Yep, so we have the carbon oxygen bond. We don't have carbon oxygen carbon. We do have an aromatic, but again, this is technical, it's specific. This is organic chemistry for you. It's the OH group is not directly bonded to the aromatic. Okay, if you had something like this, that is a phenol, but we don't have that. Okay, so this is just an alcohol. But I'm glad we're going over this because there's many different ways these molecules can look. But if you know kind of the guidelines for what is and is not, how to identify them just from looking at these groups up here, you can identify. So I think this was really good practice. Okay, any questions on that? Okay. All right, let's talk about how to name them. So again, a lot of the same rules that we already know are going to apply here, but if we're going to tweak a few things so that for this particular function group. So again, you're going to always look at what's my parent compound. Identify the longest continuous chain of carbons, all right? So the number of carbons in the ring, if it's cyclic, and instead of naming it as like an alkane or an alkene or whatever, replace the name ending with OL, okay? So that's why what you saw earlier with ethyl alcohol, we called it ethanol, okay? There's that OL ending. And that's characteristic of alcohols. You name it with an OL ending. So for example, how would we name this molecule right here? Well, let's just do the first 2 parts. We're going to count the longest continuous chain. So carbon 1, carbon 2, 3, 4, 5, 6. So if this were just an alkane, we would call it hexane, but it's going to be hexanol. Okay, well, we're going to change it. That's going to be the parent name. Now we have some substituents that we haven't accounted for yet. We'll get to that, but let's read. Well, let's look at the cyclic structure too. Then actually I want to read rule number 2 because that's going to tell us why we numbered these the way we did. Okay, rule number 2, step 2 says number the carbon atoms in the main chain. Actually, we did that. In a straight chain, the carbon bearing the OH must be assigned the lowest index number possible. So I messed up. I did it the wrong way because I didn't read rest of step 2 first, okay? So I need to number this opposite because I numbered it, and when I numbered it, this carbon right here that's bonded to this OH group, it's carbon 4, but I can get it lower if I number it the other way around. Okay, we want to give the OH group, that substituent, the lowest number possible. So this should be carbon 1, 2, 3, 4, 5, 6. So it's still a hexanol, but this is going to affect my prefixes numbering if I number it this way. So you want to try to give priority to the OH group and number it the lowest possible number. In a cyclic alcohol, the carbon that bears the OH group is number 1. So that's the example right here. Why did we put a 1 right here? Because that's the carbon that's bonded to this OH group. You always number that carbon number 1. Okay, if it's cyclic, if it's in a ring structure. Then you continue numbering in the direction that gives any other substituents the lowest number possible. So again, why did we continue numbering clockwise? Because we have this methyl substituent. We want to give it the next lowest number. If I number this counterclockwise, my methyl group is like carbon number 6. That's way too high because we can number it with a 2 going clockwise instead of counterclockwise. Okay. All right. Lastly, write the name. Place the number. Okay, place the number that locates the hydroxyl group immediately before the parent compound name. Okay, what does that mean? Place the number that locates the hydroxyl group immediately before the parent compound name. Let's go back up to this example. I know it's a hexanol. I've got to put a number, some number right here that tells me where on that hexanol the OH group is branched off. So what number should I put? Robin says 3. I agree. So it's 3 hexanol. We're still not done because we have another substituent, but we know how to do that part. If we were writing this all out, I need to move this up. So we have 3 hexanol, but I have this methyl substituent and it's on carbon number 5. So I know how to do that part. It's 5 methyl, 3 hexanol. So that is how you name a straight chain alcohol. Okay, and that's what we just did. Number all other substituents according to their positions, list them alphabetically. You guys you know how to do that. We've been doing that. In a cyclic alcohol, there's one other teeny rule. Omit the 1, specifying the location of the alcohol. So if we're going to name this guy right here, we have to give that carbon a 1, but when we write the name, we don't have to include the 1. Okay, because we know it's number 1. It's always going to be number 1. Okay, just like you guys are number 1. Okay, so how would we name this? Well, we've got how many carbons in our ring structure? 3, 4, 5, we've got 6. So this is a cyclic ring structure with 6 carbons. How do we name that? It's all single bonds. Cyclohexanol, okay, because it's an alcohol. We don't have to include, we had to put a 3 over here on the straight chain one to tell us where the OH group is. We don't have to put a 1 here, okay, that's what that rule is saying. On a cyclic structure, we know it's number 1. Okay, but we do have to tell where this methyl group is. So it's going to be 2-methyl cyclohexanol. Okay, what do you guys think about these down here? Let's do 2 more for practice. Anybody tell me what the name of this structure on the left is?
Would it be butanol?
Butanol. Anybody agree or disagree? That's what Madison says. You're missing one piece. It is a butane molecule because you got 4, and then we changed the ending to OL, so it is butanol. But what else do we have to do?
Oh, do we have to do 1 butanol since it's not a ring structure?
Yeah, we're gonna number these 1, 2, 3, 4, right? And the OH group is bonded to 1, so we gotta tell people that. We gotta tell them, oh, it's 1 butanol. That's where the OH group is bonded to the molecule. Otherwise, they don't know which carbon the OH group is bonded to. Okay, what do y'all think about the structure on the right? This one looks a little more complicated. Let's look at what substituents. Here's our OH group. Let's also, we got to number the chain too. Should I start numbering from the right or from the left?
The left.
It's funny, when y'all point left, it goes right on my
Oh,
screen.
sorry.
No, you're good. Okay, so start number field. I agree. So we want to start numbering here so that the OH group gets the lowest index number possible. So it's going to be a 2, 3, 4, 5, 6, 7. Okay, so okay, this looks deceptive. This is actually more than a heptanol. This is a 7, 8, right? I colored that though as though it was an ethyl group, but that actually is part of the longest chain. So this is an octanol. We got 8 carbons. So if it were an alkane, it'd be octane. We changed the name ending to OL because it's got a hydroxyl group on it, and that takes precedence over naming it as an alkane. Octanol, but I have to tell everybody where my OH group is bonded. So what do I need to put just in front of my octanol? Yep, 2-octanol. And then I've got to tell them where my other substituents are and what those substituents are. So I've got on carbon 4, a bromo group, and then I've got on carbon 6, a methyl group. So bromo, B comes before N. So I need to write smaller. Anybody have that issue in life? You always need to write smaller. Okay, so it's gonna be 4 bromo, 6 methyl, 2-octanol. Here's what some people would be tempted to do. Some people might name this, oh, it's a octane. And I'll just tell everybody where the substituents are. 4 bromo, 2 hydroxy, and then 6 methyl octane. But that's wrong. You name this as an alcohol. So that's why we name it as an octanol, not an octane. Okay, does that make sense?
Is the one going off the 6 carbon, isn't that an ethyl, not a methyl?
So we had to name the longest continuous chain. This looks like an ethyl group the way I color coded it. So
Yeah.
I wasn't trying to be tricky there. I'm so sorry. But that's part of the longest chain. So
So I don't name it.
instead of naming this as an ethyl group that's branched off, this is part of our longest chain, and now this is our substituent. The
Okay.
methyl group is branched off carbon 6.
Okay.
It just looks, I should not have color coded it the way I did. I wasn't thinking on that. So it looks really deceptive. I'm sorry. All right. So that's why we numbered it the way we did. Remember, you can turn corners when you're trying to number the longest chain. Okay, any questions on that? So this is wrong. We don't name it as a hydroxy group out front as though it's just a substituent. We name it as part of the parent compound, the OH group. And that's why we use the name ending OL. We're not going to name this as an octane with a hydroxy substituent. We name it as an octanol, and then we name the other substituents. Okay? Questions on that? It's definitely a little technical. Okay, for time's sake, I'm skipping over diols and glycols. It's not that they're not important. We just have other things to get to today. So jump over that. Diol is a 2 alcohol groups in a molecule, but that's pretty self-explanatory. Okay, I'm not going to give you anything about diols and glycols on the exam. So let's classify alcohols. The same way you can classify carbons as primary, secondary, tertiary, quaternary. You look at the carbon that the OH group is bonded to, and you can classify the alcohol molecule the same way, okay? So the hydroxyl bearing carbon, what does that mean? That's the carbon directly bonded to the OH group, okay? Classify if it's bonded to one other carbon. So for example, if you got something like this. So we are looking at that carbon right there, Tell me, is it primary, secondary, tertiary, or quaternary? You're counting number of carbon-carbon bonds. So this carbon right here is bonded to that carbon right there, and that is just one carbon-carbon bond. It's the only one. So we're going to call this a primary. I'm just doing a one with a degree, so that's a primary alcohol. Hydroxyl bearing carbons bonded to two other carbons. Okay, what would that look like? Like this.
Do you care on the test if we put like 1 degree or we write primary? Does it matter?
You can either write primary or put the one with the degree sign.
Okay.
Either way. Is that your question, Robin? Okay, so here's what I see. We've got this carbon-carbon bond, that's one, and we got this carbon-carbon bond, that's two. So this is secondary. So you can do that, or you can say secondary. Okay, let's continue with our pattern. Carbons bonded to three other carbons. We actually can't get a quaternary carbon with alcohols because one of the bonds is taken up by the OH group. So the highest we can go is tertiary. So it'd be tertiary. And it would look something like this. Okay, so we have one carbon-carbon bond there, 2, 3. So that's why we call it tertiary. Now, I drew all these little substituent groups identical. They don't have to be identical. Don't get it in your head that they're all going to be like methyl groups. This could be a really huge molecule. For example, right up here. If I said, okay, this carbon right here, okay, it's in a ring structure, but you could still tell me if it's primary, secondary, or tertiary, okay? Okay, questions on that? Pretty simple. Okay, let's do some things that are less simple. Let's take what we just learned. We're going to draw out the structure, and then I want you to tell me if it's a primary, secondary, or tertiary alcohol. So 2,3-dimethyl, 2-butanol. So where do you, if you're like, I don't even know where to start with this, here's where you start. Look at the parent name, bute. Bute indicates a 4-carbon chain. Butanol, 2-butanol means that off of carbon 2, I've got an OH group. I don't care if you branch it up or down, doesn't matter. Now, we got dimethyl, 2,3-dimethyl. Y'all don't even need me. They're all drawing it. Two, 3-dimethyl, 2-butanol. All right, so we're going to put a methyl group there on carbon 2. So this is carbon 1, carbon 2, carbon 3, and carbon 4. And then we're going to put another methyl group. Again, I don't care if it goes up or down. Okay, so that's, and then the rest of these bonds are hydrogen, right? If you draw it out as a condensed structure or a line structure, that's fine too. More power to you. That's the Lewis structure. So now, what carbon are we looking at? So tell me if it's primary, secondary, or tertiary.
The carbon that has the alcohol group on it?
Yes, okay, so that is this carbon right here. This is the carbon you're looking at, just this carbon. And now you're going to count how many other carbon-carbon bonds does this carbon have?
Tertiary, right?
Somebody said it.
Tertiary.
Yep. There's one carbon-carbon bond. There's another carbon-carbon bond. There's the last one. Okay. So this is tertiary. It's a tertiary alcohol. All right. 3-ethyl cyclopentanol. 3-ethyl cyclopentanol. Okay, again, cyclopentanol, that is your parent name. That's what you're going to start drawing. So that pent means you got 5 carbons, and cyclo means they're in a ring. So draw Draw a pentagon. We don't have any double bonds here. It's not an aromatic. You're just drawing a ring that has 5 carbons in it. You know, in a cyclic structure, we got this OL ending, so it's an alcohol. You put the alcohol anywhere. It doesn't matter because wherever you put it, that's carbon 1. I don't care if you put it up, down, bottom, or side. I'm just going to draw right here. So this is my carbon number 1. That's what our rule said. The OH bonded to that, whatever carbon the OH is bonded to is carbon 1. Then we got a ethyl group bonded off carbon 3. So I don't care. You determine if you number clockwise or counterclockwise. When you're drawing the structure, you get to decide some of these things. Now, if you're given a structure and you got to name it, you don't decide these things. You read the structure. But here, I don't care if you bond it over here or over here. Okay, if you number this way, then this is going to be carbon 3. But if you number counterclockwise, that's going to be carbon 3. So there's 2 acceptable structures here, but I'm just going to pick one. Okay, so we're going to say this is our ethyl group. So it'll be a CH2, CH3. And again, you could draw it as a line structure. You could draw out all the hydrogen bonds. If you just draw it as a line structure, it looks like this. So OH, and then boom, boom. Okay, that's my ethyl group. And there's OH, and this is my carbon 3, that's my carbon 1. So now tell me, is this primary, secondary, or tertiary? Robin?
Oh, I just have a question. So when
Yeah.
I CH2, CH3, do I have to bond? Do I have to do the bond in between the middle of the CH2 and the CH3? Or can I just write it CH2, CH3?
That's fine.
For my-
That's fine.
Okay, just want to make sure.
Now, if you draw the line structure, it's got to look like what I drew. But, all right, so somebody tell me, we're looking at, there's a carbon right here. Is that primary, secondary, or tertiary? Robin says secondary. What do y'all think? You just nod your head, yes or no? All right, secondary. Yep. We got carbon bond there and a carbon bond there. Okay, I'm gonna let you do these for practice on your own. We gotta move on, but there's some more practice with this. I didn't tell you to do the primary, secondary, tertiary part on this question over here, but that's great practice if you want to add that to it. You draw it out, and then you can tell me if it's a primary, secondary, tertiary alcohol. Okay, a little more practice though. I'm gonna pick, we're gonna do A and B. Don't try to name this. This is a diol, okay? Actually, it's a glycol. So now, because I decided we're not doing those, don't waste your time on doing D. All right, so how would we name A? We'll try to name this. Well, we got to number the longest continuous chain. It's right here. We got a 3-carbon chain. So what's the root word?
Prop.
Prop. So this is it's not propane because we got an alcohol. So it's propane, take the E off and change it to OL, propanol. But we got to tell everybody where the OH group is bonded to. It is bonded to the 2nd carbon. So I'm going to scoot propanol over. So this is 2-propanol, but we're not done, are we? We have this methyl substituent branched off, also carbon 2. So this is 2-methyl, 2-propanol. Okay. All right, B. Somebody tell me, y'all look at that. Somebody tell me how you would name this. First thing you do is figure out what's my longest continuous chain, and it has to include the OH, the carbon that is bonded to the OH group. We call it a hydroxyl bearing carbon.
Would it be butanol? Do you start with the carbon that's connected to the OH?
Right here. Remember that carbon 1? I like that idea. Where do we number from there?
Oh, so would it be pentanol?
That would be 2. That would be 3. If I go this way, I'm dead ending my structure, 4. But I think I can make it longer if we go 4, 5. So yeah,
You
5
wouldn't
is,
you won't start in the OH group. So where 2 is, that wouldn't be 1.
no, this carbon right here is carbon 1.
Okay.
So it is pentanol. So instead of pentane, okay, you could write out pentane if you want, but remember, if it's an alcohol, you take off the E and you name it OL, pentanol. All right, so it's 2 pentanol. Why? Because I'm telling everybody where the OH group is. It's bonded to carbon 2. And then I gotta, what is this right here? How do I write that?
Is that 3-methyl?
It is. It's a methyl group. Okay, there'd be a CH3 right here. You can draw it in if it helps you. Okay, so it's bonded to carbon 3. So we just say 3-methyl, 2-pentanol. Okay.
I get confused because I don't understand why there wouldn't be, yeah, it's bonded off 3, the methyl right here, but why is it not bonded off 1 and 5 too?
Oh, okay. So Robin, because 1 and 5 are part of the main chain,
Oh,
I determined that this right here is my longest chain of carbons. Okay, so those carbons are included in this word pentanol. It's a 5-carbon chain. So that's carbon 1, 2, 3, 4, 5. If it helps you, Robin, we could draw this all out in a straight line and get the same molecule. You could literally draw this out like this. And say, okay, carbon 2's got my OH, carbon 3 has my CH3. And then you draw all the hydrogens in. It's just in a line structure, things can be curved and turned like this. Does that help? Okay. All right, I'm gonna let y'all do C on your own. That one looks really fun though. Okay, properties of alcohols. So let me zoom out. So we've already looked at the fact that alcohols have relatively high boiling points. That was like the second or third slide. Okay, we said the boiling point of this alcohol is similar to the boiling point of water. It's pretty high, a lot higher than corresponding alkanes and corresponding ethers. But here's a question: are alcohols polar or non-polar? Okay, this kind of seems like a trick question. The answer is that alcohol molecules have both hydrophilic and hydrophobic portions. Okay, they have portions that are electronegative. Okay, that oxygen OH group. Oxygens are very electronegative. Y'all remember what I mean when I say electronegativity or electronegative. Elements that are close to fluorine on the periodic table are electronegative. They attract electrons. So we give these different colors like the red and the blue. Okay, so that's an electronegative portion. But then you've got this hydrocarbon portion right here. I guess I should circle all of it. All of this is a hydrocarbon portion. And this part is nonpolar. This part is polar. If it's electronegative, usually polar. All right, so they're both. They have parts and portions that are each polar and nonpolar. This is 1 propanol. Now, I also wanted to write this out. Because of that, there's 2 things to always note with alcohols. Okay, there's an electronegative region. It's got some electronegativity. That's the polar part. And then it can hydrogen bond. It can hydrogen bond. In fact, I'll show you how this can hydrogen bond. All alcohols can hydrogen bond. You've got lone pairs on your oxygen. These are the acceptors. I'm going to put an A for acceptor. And this hydrogen right here is positively polarized. And this is the donor, D for donor. So a water molecule comes along. The hydrogen on the water molecule, these are both positively polarized. Lone pairs on the oxygen. You could get a hydrogen bond right here. Okay. If another water molecule came along, it could hydrogen bond with that lone pair. And then the lone pairs on the oxygen from the water molecule could hydrogen bond with the positively put the donor on the one propanol molecule. Y'all see all the ways it can hydrogen bond? Okay. So what does that mean? If it's both polar and nonpolar, how do we know what it's going to do? Is it going to be soluble in the body? Because our body is mostly water, okay? Our blood and everything else, aqueous environment, and our cells. So it's going to be soluble in aqueous environment. Is it water soluble? Is it going to be soluble in nonpolar solvents? How do we know? Well, alcohols are they're not as straightforward as like alkanes and alkenes. So basically what happens, the larger the hydrocarbon part is, so basically this. So if we had this chain extending, if it's really long, the larger that is, the more alkane, whoops, spell it right. Alkane-like, the more alkane-like it is. Okay, alkanes are nonpolar. So the longer this hydrocarbon portion is, the more nonpolar the molecule becomes. The nonpolar region kind of takes dominance and directs how the alcohol behaves. And the less water soluble alcohols are. Does that make sense? We call hydrocarbon, so hydrocarbon portions of molecules. This part that I said that was nonpolar. This would all be hydrophobic, okay? Things that are nonpolar, if they're hydrocarbons, they're hydrophobic. And y'all know what that means, hydrophobic and hydrophilic. Hydrophobic is water-fearing, hydrophilic is water-loving, all right? So the longer the hydrocarbon part is, the more alkane-like and the less water-soluble the alcohols are. But how do we know, like, how does it work depending on, how do we know where the cutoffs are? Like, is it going to be water soluble if there's only 3 carbons, or is it 5 carbons, or if there's 12 carbons? How do we know when it is water soluble and when it isn't? Well, there is kind of a ratio we can judge by. If the carbon oxygen ratio, so let's erase all this long tail I drew. We know just from looking at one propanol here, what is our carbon oxygen ratio? Well, I've got 1, 2, 3 carbons, and I've got 1 oxygen. So that is a 3 carbon to oxygen is just 1 oxygen. So that is, if our ratio is a 1-to-1 or a 3-to-1, meaning 1 carbon, 1 oxygen, all the way to 3 carbons, 1 oxygen. That's my ratio. So that's either ethanol, methanol, ethanol, or propanol. These are soluble. Okay, because the hydrocarbon portion is pretty small. But if your ratio becomes 4-to-1, so now we're talking about butanol. You got 4 carbons in the molecule, only 1 oxygen. There is slight solubility. So it's slightly soluble. But if that hydrocarbon is longer, meaning 5 carbons in the hydrocarbon portion or even longer, so pentanol, hexanol, heptanol, or greater, it is not soluble. So alcohols are like really high maintenance, okay? It depends what the rest of the molecule looks like. So their properties depend on the size of the alcohol. Does that make sense? So here's the deal. This seems pretty technical. I'm not gonna split hairs on this, but I do want you guys to know if I said something like, is methanol soluble in water? Or is octanol soluble in water? Okay, based on this stuff, you could definitely answer that. We're gonna skip the next, any questions on all of this? Anybody still writing? Okay, we're gonna skip over this slide because it's all diols and triols. Okay, the more OHs you have on your molecule, the more soluble it is, okay? So for example, if I had like, well, we're actually gonna get to a practice problem on that in a minute. But Anyways, we're gonna move on. Table 14.1. This is just a handy table. I really like it because it shows you different alcohols like methanol, ethanol, isopropyl alcohol. What is isopropyl alcohol used for? That's rubbing alcohol. Okay, you go buy a bottle at the store at Walmart, that's what's used. Rubbing alcohol. So it just tells you some of the common properties and applications. Do not sit here and memorize everything on this table. But I will say glycerol is really going to become important later on. When we get to fatty acids, glycerol is important. Now look at glycerol. How many OH groups do we have here?
3.
Yeah, so we call this a triol. Tri meaning 3, all meaning 3 OH groups. You look at propylene glycol right here. Okay, notice the name ending diol, D-I-O-L. There's 2 OH groups. So di, the prefix di means 2. The prefix tri means 3. Okay, so the more OH groups you have on something, the more polar it is, the more soluble in water it is, the higher the boiling points, because the more hydrogen bonding you can get. That makes sense? So anyways, I think actually, yeah, I have a poll question on this, what I just said. We'll launch a poll question because we talked about physical properties, boiling points. Where is it? Yeah. So I want you to look at these. No rush here. I want you to look at A, B, C, and D. I want you to rank them. You need to take into account, okay, how many carbons, how many OH groups. The more OH groups you have, the more hydrogen bonding it can do, and the more heat it would take to break the hydrogen bond apart and cause it to melt or boil, okay? So which one would have the highest? You pick that one first. And which one would have the lowest boiling point? You put that one last. But you also may have to take into account the carbon-oxygen ratio, like we said. No, actually, really don't have to do that here. Okay, we're missing one vote. Okay, in the poll. So we got some different results. It seems like DBAC was the most popular one. So I'm gonna look at A. Here's what I noticed. I've got 1 OH group. Okay, B, I've got 2 OH groups. C, I have 0 OH groups. D, I have 1, 2, 3 OH groups. And everything has 3 carbons, okay? Everything has 3 carbons. Those carbons might be spread out, but everything has 3 carbons. So we're gonna order this. Highest boiling point has got to be D, because it has the highest number of OH groups. So that means it could have the largest amount of hydrogen bonding. So it would have the highest boiling point. The more hydrogen bonding, the higher the boiling point. So D for sure is going to have the highest. Then B is going to be our next highest because it has 2 OH groups. A is going to be next, and then C because C has no OH groups. So C cannot hydrogen bond at all. Okay, so this for sure is a very plausible exam question. I want you to be able to order things like this by their boiling or melting. Melting point would have the same trend. You put the same answer. Any questions on that? Okay. So we're a decent ways in. So far today, we've learned how to identify alcohols and how to name them, whether they're straight chain or cyclic. Oh, Abby just asked a question. You asked it a while ago. I'm just saying, do we see any different because the OH is bonded? Abby, did I ever answer your question? Okay. So sorry. interrupt me if I don't answer your questions. Okay, we learned how to name, identify alcohols, phenols, and ethers. We've learned how to name them. And then we've also looked at properties associated with alcohols and how that relates to other alkanes and ethers as well. Now we're going to talk about reactions of alcohols. Okay. Let me see how many slides we got left. I'm trying to judge where we are. We are right here. We're about halfway through. Okay, we got 30 minutes left. So let's get through reactions. The first kind of reaction we're going to talk about with alcohols are dehydration. So just the name in and of itself, dehydration. What do y'all think that means? We're going to be taking a water molecule through the loss of a water molecule. Way this happens, so an alcohol has an OH group bonded to one carbon and then hydrogens bonded to other carbons. So we're going to lose the OH group, we're going to lose the alcohol functional group, and we're going to lose a hydrogen from an adjacent carbon. Okay. You do have to, this does not happen unless you have a strong acid catalyst. Okay. And what it forms is it produces an alkene. So it's kind of the opposite of what we did yesterday. Yesterday, we took an alkene and we looked at hydration reactions where we made alcohols. Today, we're doing the opposite. When you have an alcohol, that reaction can go in reverse with a strong acid catalyst. We're going to take the OH and the H off. That's going to make water. And then one electron from that bond and one electron from that bond are going to come together to form the double bond, the other bond of the double bond. And that's what makes the alkene, because now you have a double bond between these carbons. And we know we name that as an alkene. Okay. Now, sometimes there can be multiple adjacent carbons from which the H can be lost. And you know what? I wish I didn't, but I do need to go over this. So basically, let's look at this alcohol right here. We got a butanol, 2-butanol. Okay. So this is carbon 1, carbon 2, carbon 3, and carbon 4, 2-butanol. And we've got our strong acid catalyst. So we're going to take this OH group off, but the question is the hydrogen going to come off of carbon 1 or is it going to come off of carbon 3? And you're like, who gives a rip? Organic chemists give a rip. Okay, basically look at what you form. If you do this reaction in the lab, you're going to get 2 products, but you're going to get one in much greater amount. 80% of your product is going to be this one, where you pull the hydrogen off of carbon 2. And the double bond is now between, this is carbon 1, this is carbon 2, 3, and 4. The double bond is now between carbons 2 and 3. So we call that 2-butene. 80% of your product is going to be that. Only 20% is going to be the other product where we're pulling a hydrogen off carbon 1 butene. Okay. So why is that? Well, this explains it. The hydrogen will be removed typically from a more internal carbon so that the product alkene is a higher level of substitution. What does that mean? Well, we know substitution refers to how many other carbon-carbon bonds you have. So when we pull the hydrogen, when we pull the hydrogen off of this carbon, we're left with a carbon group, a methyl group bonded to that carbon, and a methyl group bonded to this carbon as well. All right, so that's a higher level of substitution than this alkene, which only this carbon has other carbon bonds. This carbon doesn't have any. So 2-butene has a higher level of substitution than 1-butene. So that's why basically we're going to be pulling, just pay, if you get confused on this, reread this. This will tell you where to pull the hydrogen off from. We're actually going to do a practice problem. It's going to be removed from a more internal carbon. So let's do a practice problem on this, and maybe that will make more sense. What product would you expect from the following reaction? We got an alcohol here. Okay, so am I going to pull a hydrogen off of here or off of here? So you could actually, what would help, I think, is to go through, let's look at these 2 carbons. Okay, let's look at, this would be carbon 1, carbon 2, and carbon 3. Look at carbon 1 and 3. And go ahead and label these carbons as primary, secondary, tertiary, or quaternary. And then whichever one has a higher degree, you're going to pull the hydrogen from that carbon. Carbon 1 here is primary. Carbon 3 is tertiary. So because it has a higher level of substitution, we're going to pull the hydrogen off that. So basically, this hydrogen right here, I'm going to highlight it. This hydrogen right here and that OH group right there is going to go. That's what it's going to be. This is a dehydration. That's the water molecule. It's going to be pulled off. And then we're going to form a double bond. Between carbon 3 and carbon 2. So this is the product we would get. Does that help make sense, what I was trying to explain on the previous slide? Okay. The reason I'm taking the time to do this, I think you have some problems like this on your homework for chapter 14. Okay, the next problem says, any questions on that? Seriously.
Wait, so how did you get a double bond?
All right, thank you, Cameron. What happens, I'm gonna go back up here. When you get the double bond comes from the fact that we're taking, you take the OH group off of one carbon and you take a hydrogen off of a neighboring carbon. And if you have multiple options to take the hydrogen from, like different carbons you could pull a hydrogen from, you're gonna take it off of the carbon that's like a higher level of substitution. So like you would take it off of a secondary or a tertiary carbon before you take the hydrogen off of a primary carbon. Okay, so the double bond comes from removing a hydrogen and an OH group from neighboring carbons, and the electron, one electron from each of these bonds comes together. We know bonds are made of electrons, and they form this double bond right here. Now, you're not going to have to draw electrons and arrows for me, but you do need to be able to write the product. So I think let's do some more practice, and then if anybody still has questions after that, please stop me and we can walk through this again. Okay, what alkenes might be formed by dehydration of the following alcohols? Okay, so basically just saying, if we have an acid catalyst such as H2SO4, what product are we going to get? So we know we're going to take this OH group off. And we only have one option to pull the hydrogen off of. This carbon only has one neighboring carbon. So we have to take one of the hydrogens. One of these hydrogens has to go. Okay, so when we draw our product, we're going to have CH3. That part is unchanged, that part of the molecule. But if we take a hydrogen off of this CH2 group, what's left? If we take one hydrogen off of this CH2 group, what's left?
Is it just CH?
Just CH. Okay, so then we're going to have our double bond right here. We took the OH group off of this from that carbon, so then we got CH2. Okay, this might help if you draw everything out. So I'm going to draw the molecule of A over here. We had this C. We have a CH3, then we have a CH2, then we have another CH2. I'm going to draw the OH group down here. Okay, so what we're taking off is this right here. Taking the hydrogen off that middle carbon and the OH group off the end carbon, and we're forming a double bond right there. So you just literally erase this, and that's your product. That's what we drew, CH3, CH, CH2. Is that clicking?
Is this what we're doing in our pre-lab?
On the pre-lab, you're doing like halogenation and what was the other one? This right here. Halogenation and oxidation. So this is like what we did yesterday. Okay. We did example problem of that yesterday. This, we actually haven't looked at an example of that yet. We're about to. Okay. So not quite, Cameron, but we did do bromination or halogenation reactions yesterday. But again, after lecture, pause me or catch me if you want to talk through any of this. Let's look at another example. B. What product do we get? Okay, so we're reacting this. We got a strong acid catalyst. We're going to we're going to dehydrate this alcohol. So the carbon bonded to the alcohol is right here. And basically, I got two options. I got a carbon that has two hydrogens here. And I got a carbon that has two hydrogens here. So I could pull a hydrogen from either one of these carbons. They're the same level of substitution. Both of these carbons are secondary because you got a carbon-carbon bond here and a carbon-carbon bond there. You got a carbon-carbon bond here, carbon-carbon bond there. I guess I could highlight it. There's a carbon-carbon bond, there's a carbon-carbon bond, there's a carbon-carbon bond. So both of these are secondary. So it doesn't matter which one I pull the hydrogen from. So you're going to get one product. Well, you could draw it two ways, but they're actually identical. So the OH group is going to go, and you're either going to get a double bond there, or you could draw it like this. You're going to get a double bond there. Okay, so what I did is I said, we're going to take that off, and either that hydrogen is going to go, and you get the double bond, okay, right here. Or we take a hydrogen up here off, and you get the double bond angling up. So what happens when you dehydrate an alcohol, you get a what? What product do you get? These are all, what kind of functional group do we have in our product?
Alkenes.
Yeah, if you write down one thing today, dehydrating an alcohol forms an alkene. Dehydrating an alcohol forms an alkene, okay? Dehydrating an alcohol, taking an OH and a neighboring hydrogen off, you get an alkene. And I would say it'd probably be really good, and if anybody wants to do this with me on an office hour today or tomorrow, to sit down and make statements like that for all the reactions we talked about. Halogenation forms an alkane or whatever. Hydration of an alkene forms a alkane, things like that, okay? Because it helps me when I have statements like that in my head to remember what each of these kinds of, there's so many reactions we've already covered and more that we're going to cover. It can be confusing. Okay, last one. Y'all tell me what I should draw for this product. If you're looking at this, we're going to take this OH group off, and we can either take a hydrogen from right here, or we can take a hydrogen from right here. Remember, you're looking at the neighboring carbons, so from that one or from that one. Anybody?
I think I might have it. I don't know.
Okay, what should I write, Max?
I did CH3
Yeah,
connected to CH
yeah.
and double bonded to CH with a methyl group off of it.
Go one more. That's where it is.
And one more over. Oh, okay.
So you were
Oh, I
super close.
see. Oh, okay.
Yeah, that's it. So what we're gonna do, what happened here is we pull the OH group off and we take one of these hydrogens off. Okay? So again, if it helps you to draw the Lewis structure out and really see what's going on, you got CH3, and we have a CH, we had the OH pointing up, and we have a CH2, and then we got a CH with a methyl group and a methyl group. This is the molecule, but that's the Lewis structure. So we are literally just going to take off the OH from here and the hydrogen from here. Why? Why are we not going to take off any of these hydrogens? Because this is a primary carbon and this one is a secondary carbon, higher level of substitution. You take a hydrogen from the carbon that has a higher level of substitution. You're going to take a hydrogen off of a secondary or tertiary carbon before you take it off of a primary carbon. Okay, so we're taking these away and you're going to get a double bond here. So when you write out the condensed or the line structure, however you want to draw it, you should get this. CH3, CH. Okay, so this is the molecule that you have left.
Question.
Yes, Robbie?
On the test, is it okay, like, if we just write both? Like how you're supposed to take it off the, higher one? Is it
As
okay?
long as I'm clear on what your final answer is. Does that
Okay,
make sense? As long as it's clear to me what your final structure answer is, then you draw whatever else you need to draw, circle your final answer or whatever.
okay.
Okay, so that's dehydration. Oxidation, this is the other big reaction. I think there's only two big reactions today. Dehydration was one, oxidation's the other. So I need to pause and define something for a minute because you guys talked about redox reactions in whatever chemistry class you took previous to this, okay? And redox is never anybody's favorite, but man, they are such a huge part of our biochemistry. We would not be alive without redox reactions. So I need to redefine oxidation and reduction for a second. So in organic chemistry, probably what you had previous, we define oxidation as losing electrons. Did anybody ever hear the acronym oil rig? What that stands for is oxidation is the loss and reduction, I'm going to abbreviate, is the gain of electrons. So oxidation is the loss of electrons. Reduction is the gain of electrons. And that's previously how we defined redox, okay? But now we're gonna expand that definition. So that is all true, but we're gonna expand it. Oxidation and reduction can also be other things. So for organic chemistry, what we're in, oxidation could be this, increasing the number of carbon-oxygen bonds. So for example, if you have a carbon-oxygen single bond and it becomes a carbon-oxygen double bond after we do something to it, that carbon was oxidized or that molecule was oxidized, okay? So increasing the number of carbon-oxygen single bonds and or decreasing the number of carbon-hydrogen bonds, okay? Either of those things is oxidation. Now, I know that's not sinking in yet. We are going to practice this. Reduction can be the opposite, decreasing the number of carbon-oxygen bonds and or increasing the number of carbon-hydrogen bonds. So if you react something with your molecule and all of a sudden you go from a carbon single bond to a carbon-oxygen, so carbon-oxygen single bond to a carbon-oxygen double bond, that's oxidation. If you have a carbon-oxygen double bond and it becomes a carbon-oxygen single bond or the oxygen completely goes away, that's reduction. So we're going to look at several examples of this. Now this happens in our bodies, this happens in the lab with oxidizing and reducing agents. You have to add something to the reaction for this to happen. And we're going to see this today in lab, compounds like this, potassium permanganate, okay, these chromate compounds, or even oxygen. Oxygen is the simplest oxidizing agent, okay? So we symbolize them as O. So if you see a reaction or an arrow like this with an O above it, we don't know what oxidizing agent's being used. We just know that something is going to be oxidized. We're using some kind of oxidizing agent, okay? Okay, let's break this down. How does this apply to alcohols? How do we oxidize an alcohol? All right, let's look at this molecule right here. This is an alcohol. Why? Because I have a carbon bonded to an OH group. It's an alcohol. Now, if we oxidize this, we react it with some sort of oxidizing agent, what happens is that these hydrogens come off. They just are ripped off by the oxidizing agent. Okay, oxidizing agents love to be reduced. So it's going to rip the hydrogens off, and you're going to form this carbon-oxygen double bond. We call this a carbonyl compound. And the hydrogens, they go away. They're bonded to the oxidizing agent. Okay, so notice 2 hydrogens are removed from the alcohol. 1 hydrogen is taken off from the OH group, the hydroxyl group. And then 1 hydrogen is removed from the carbon that bears or is bonded to the OH group. All right. So let's break this down. We know we can have primary, secondary, or tertiary alcohols. You're going to get slightly different things depending on what kind of alcohol you have when you oxidize it. So if we have a primary alcohol, and after we talk through these 3 things, we're going to take a break. We have a primary alcohol, okay? So that means this carbon right here, it just has 1 other carbon-carbon bond, all right? That's why it's primary. So that's a primary alcohol. We're going to take, when we oxidize it, we're going to take these hydrogens off. What do we form? Well, this carbon still has the bond to the other R group, which is some sort of carbon alkyl group, and it's still bonded to this green hydrogen. That part does not change. What does change is that this carbon is now double bonded to the alcohol, or sorry, to the oxygen. And what functional group did we form? An aldehyde. This right here is an aldehyde. Remember, a carbon double bonded to an oxygen. We call that a carbonyl carbon. When the branched off substituent is just a hydrogen, that's the simplest it can be, we call that an aldehyde. All right, so these 2 hydrogens go away, and 1 electron from here and 1 electron from here go to make this double bond. You are not going to have to draw the electron parts out for me, but if you're like, where does this double bond come from? That's where it comes from. So by the way, this is step 1. This is step 1. This is if you just have mild. That's not how you spell mild. We could keep going. If we have a strong, so if we do more oxidation, so this would be like strong. If we strongly oxidize a primary alcohol, we are going to take off this hydrogen here, and we're going to substitute it with, we're going to form another carbon-oxygen bond. Okay, we're actually going to bond an OH group to it. And what that forms is a carboxylic acid. This right here is a carboxylic acid. So a primary alcohol mildly oxidized gives you an aldehyde. Strongly oxidized, you go all the way to a carboxylic acid. You see how on a primary alcohol, we just had 1 carbon-oxygen bond. After we oxidize it, we have 2 carbon-oxygen bonds. It's in the form of a double bond. And then after we strongly oxidize it, we have 3 carbon-oxygen bonds, a double bond and a carbon-oxygen single bond. So we are increasing from 1 to 2 to 3 the number of carbon-oxygen bonds. And that's what we said, increasing the number of carbon-oxygen bonds. That is why we call it oxidation. Okay. This is very different from the kind of redox we did in the previous chemistry class you may have had. Okay, that's primary alcohols. Really quickly, secondary alcohols. So a secondary alcohol has 1, 2 bonds to other carbons. That's why we call it a secondary alcohol. Same thing is gonna happen. We're gonna take these hydrogens off. When we oxidize it, there's our oxidizing agent. We're gonna take the hydrogens off, and one electron from here and one electron from here go, and they form this bond, so we get a carbon-oxygen double bond. And what functional group did we just make? A ketone. So basically, the statement here is that oxidation of a secondary alcohol produces a ketone. No further oxidation can take place. So primary alcohol, you could strongly or mildly oxidize it. If you mildly oxidize it, you end up with aldehyde. If you really strongly oxidize it, we said carboxylic acid. But with a secondary alcohol, there's only one option here. When you're done oxidizing it, you get a ketone. So we have increased the number of carbon-oxygen bonds from 1 carbon-oxygen bond to 2 carbon-oxygen bonds. Okay, it's just that this is in the form of a carbon-oxygen double bond. So that's why it's oxidation. Tertiary alcohols, we only have 1 hydrogen. We don't have a second, we got to be able to take 2 hydrogens off. And so because we don't have any other hydrogens down here that we can pull off, we don't get a reaction, no reaction. Okay. Because there is, excuse me, no hydrogen on the carbon atom attached to the OH group, tertiary alcohols do not react with oxidizing agents. Okay. So, all right, we need to